Okay, so we've spoken about alpha, beta and gamma radiation, and I want to talk about something called the activity. So if we have a radioactive source, it is emitting radiation, be it alpha, beta or gamma, and every time it emits an alpha particle or a beta particle or a form of radiation, it undergoes a change. Its nucleus, the nucleus of a single atom in here that emits radiation, will now change, and that is called the decay of a nucleus. Okay, so every time a nucleus spits out a form of radiation, the nucleus decays. So if you start with n atoms and n2 is the number that decay, then the activity is known as, or is defined as, the number of decayed atoms per second. Okay, so it's the number of nuclei, or atoms or nuclei, I guess, nuclei that are decaying per second. So the activity might be, in this case, if n2 atoms decay in a time t, then the activity is the number of atoms that have decayed divided by the time. It's the number of atoms decaying per second. And the unit then is, if you think about it, n is just a number, so it doesn't have a unit, and time is seconds. So 1 over seconds, or seconds to the power of -1. But that has a name. Its name is the becquerel, after a scientist, but it's shortened to BQ. So more often than not, the unit of activity, which is the number of atoms decaying per second, the unit of that is the becquerel. And 1 becquerel is the unit, 1 becquerel means that 1 atom or 1 nucleus is decaying per second. So if something has a unit, if an activity is 1 becquerel, that means that there is 1 nucleus decaying per second. The law of radioactive decay, so the law of radioactive decay states that the activity, or the number of nuclei decaying per second, is proportional to the number of undecayed atoms. So that's the number of undecayed atoms. So the activity is proportional to the number of undecayed atoms. So in other words, if you have a lump here and n is the number of atoms that have not decayed, then the number of atoms that are decaying per second depends on that value n. Okay, and that's an important fact. That's A is proportional to n, and the constant of proportionality is A is equal to lambda n, where lambda is known as the decay constant. Now, lambda is a constant for a particular isotope. So a particular isotope will always have the same decay constant, but different isotopes will have different decay constants. Okay, and again now, if you were to think about it, A is seconds to the -1. Okay, so the decay constant is the number of undecayed atoms, the decay constant would be the activity divided by the number of undecayed. So it will have the same unit. In other words, this has no unit, so the decay constant has a unit of seconds to the -1. Okay, so that's a very important one. We'll put that up in the top corner. A equals lambda times n. The activity, the number of nuclei decaying per second, is equal to a constant times the number of atoms that are actually undecayed at that instant. So in other words, the activity is constantly varying because the number of atoms decaying is constantly varying. Okay, if you actually have a look at both the number of atoms decaying per second, or sorry, not the number of atoms in a material, and you look at it over time in seconds. So we have a lump material that has initially got, we'll call it N0, undecayed atoms. So N0 is the number of undecayed atoms. And as time goes by, obviously atoms are going to spit out radiation, okay, or nuclei are going to spit out radiation, so they are going to decay. Every time they spit out, they have decayed, and you have a smaller number of undecayed atoms left behind. So the number of undecayed atoms, N, will start at an N0 and it will decrease. It decreases exponentially, and that's really important, and you need to know that it decreases in an exponential way. And what's also true is that the time that it takes for the original number in a sample to half, the original number of undecayed atoms to half, that time is known as the half-life, the number of seconds that takes. And now you're starting with N over 2, N0 over 2, so the time that it takes for that number to half, to N0 over 4, is T a half again. So the time that it takes for a particular number of atoms to half, in other words, half of them will decay and you're left with half of them, is this T a half, which is called the half-life. Okay? And the half-life, T a half, is worked out mathematically, and it is found to be the log to the base E of 2 divided by the decay constant. Now, the log to the base E is also written as ln2, so you could see it written like that. So, up here, the half-life is ln2, or the log to the base E of 2, divided by the decay constant. So now you have two formulas linking all of these together. Just to point out, if you were to draw a graph of the activity over time, because the activity is just a constant times n, then the graph of n over time and the graph of activity over time are almost identical. This is just, A is just this, the graph of A, the y value here at any point is just the same as the y value here multiplied by a constant. Okay, and if we call A0 the original activity, then the time that it takes for the original activity to half is also the half-life. And again, for that in turn to half, and so on. Okay, so again, just to think about what you're saying there, basically the number of atoms decaying per second is a certain value at the start, and after the half-life, the number of atoms decaying per second is now half. So we have our rate of decay is changing all the time. Okay, and that is because A depends on N directly. So if N is changing, then A is changing in a similar way. Okay, so make sure you know that both graphs, activity over time and the number of atoms that are undecayed over time. Remember, N stands for the number of undecayed or kind of undecayed nuclei or atoms over time. Okay, so be aware of that. I'm going to do questions now. I think I've covered everything there, so I'm going to now do the examples in the book, and then you guys can do the questions for homework. But I'll do it on a different video because it'll take too